Attention is very fundamental architecture in transformer model. Of course, GPT-X has this architecture, transformer model architecture. So, in order to understand the basic architecture and principles associated with the GPT-X, we have to talk about attention. Attention is all you need is the title of paper published a few years ago to talk about GPT-3 and GPT-2. So the main focus of the class today will be about attention. This is very simple representation of transformer model. Transformer model has two different structure. First one is encoder, and second one is decoder. Basically, transformer model has encoder and decoder architecture. You have sequential input x1 to x2. Important feature of transformer model is that you put the input is in sequential data, like recurrent neural network. Usually our text or voice has certain sequence of words. So initially this transformer model was developed as a large language model. And language has sequential input. So if you write a sentence or a block of sentence into the transformer model, those will be input to the encoder. And of course, eventually, you're going to have output sequence. Input sequence may have a certain number of wordings. T could be 1,000 or 10,000 or millions, depending on your computer size and depending on your parallelization of GPU and HBM. In RNN, you remember that previous state was carried to next stage through a multiplication of W matrices. So previous information was carried through the hidden layers sequentially. But surprisingly, in transformer model, all this input was given to encoder in parallel. In RNN, you have long time to compute output because each hidden layer has to be connected sequentially. The connection between previous hidden layer and next hidden layer was defined by W matrices. So in order to complete the input process, you have to take a huge number of input processes. But when you are using GPT-X, if you finish your typing of your question or whatever, it goes in parallel simultaneously. That is the big difference between our previous large language model like RNN with transformer. Why these transformer model are pursuing parallelism? Because it wanna give you the output simultaneously, real time. People are not patient enough. If I wanna talk to the AI, if I give a question, we expect to receive the response in a millisecond, something like that. If it takes a second or a minute, we are not patient enough, or we cannot think AI as a kind of humans. So let's assume that millions of people in the earth are trying to use generative AI, transform model, and each of the individual want to talk to the AI. They want to have response in a millisecond. So sequential model like RNN may take too much time. So scientists and engineers in probably OpenAI want to develop real-time AI. Because of that, encoder operation is a kind of parallel computing, not serial. Because of that, we need more GPU and more HBM. GPU has certain parallelism in terms of computing, and HBM has certain parallelism for storing and sending data like that. CPU is not suitable for parallel operation. It's more suitable for high-speed serial operations. So future direction of AI semiconductor memory and supercomputer are being developed into the extreme parallelism, like millions or million parallelism. So number of interconnection and number of cores and number of memory cell has to be connected in parallel, and number of parallelism could be a millions or 10 millions like that. So AI semiconductor and supercomputer architecture might be completely different from the previous semiconductor and AI supercomputers. So one important feature of this transformer model is in parallelism. Now, output of encoder is connected to decoder. And this connection is called cross attention. Let's assume that you have 1,000 input and 1,000 output. The relationship between output and input has to be defined by a certain way, and there is a matrix representation that make a connection between encoder and decoder. Inside encoder, you have parallel input, like more than 1,000. We have to learn what's the relationship between X1 and X2 simultaneously. That kind of relationship between serial input is represented by self-attention. So, number one feature of transformer model is parallel input and probably parallel output in the future. But unfortunately, at this moment of stage, decoder output is serial. Sometimes in the future, probably GPT-5 or 6, decoder may have also parallel output. All the text. Let's assume you input the English and the translation is Korean. This generation of decoder may be in parallel as well, not right now. Then you put in whole book of Korean book, whole book may be translated into English in a millisecond. Right now it takes longer because decoder is not parallel yet. Number two important feature of this transformer model is attention. Attention is a relationship between words. let's assume you have a whole book from the beginning to end. You may have millions of wordings. And somehow some wordings has a more important connection than others. And that amount of importance or relationship between wording will be represented by attention. Inside encoder, we have certain attentions, and between encoder and decoder, we have input sequences and output sequences. We have some connections, and the degree of connection between word sequencing and output sequencing is defined by attention. So attention enables us to make a parallel connection. Also, attention gives us some long-term memory effect. In the RNN, the first wording and second wording has different impact to the output because input will be multiplied by W matrix and W matrix through the hidden layers, and some of the effect will be diminished at the end. But by using the attention, it is directly connected from first wording to the last wording. Of course, it takes a lot of computational power to train those connections. That is the main purpose of the training process of transformer model. Third one is positional encoding. When you are actually, this is a text, you may have certain text and you have to make an input to the encoder, so you may have to have certain translations. And in this transformer model, each x1 to x2 has some information included, position information. In the language, position has important role. Depending on position of each word, meanings are completely different. So when we are put our real text to the input embedding, we are adding some positional information into the code. That is called positional encoding. I'm sure that it is a little bit difficult for you to follow at this moment, but after 3 classes or 4 classes, you may be able to follow me. Right now, I want to give you the overall perspectives of transformer model. There are 3 important features. Basically, it is encoder-decoder architecture. And to make a real-time generation, we are pursuing parallelism. That is the very important feature of this transformer model. Second one is to make a connection between wordings in the text or in a book. We need an attention mechanism. And this is also a very important feature in transformer model. Third one is we have to add some positioning encoding at the input. Among this parallelism, these are very important for computing. So when we are designing your semiconductor memory or supercomputer, this parallelism is very important feature. But in terms of transformer model, this attention is uniquely different from previous sequential model like RNN. So that's why the paper who is introducing this transformer model at the first time, the name of the paper was "Attention is all you need." Let's move on one by one. There are 2 types of encoder. First one is encoder self-attention. You may have input wording x1, x2, and xt. we want to make a map of relationship between words. This yellow line is self-attention. How are you gonna score these attentions? Let's assume I'm a boy. Jungmin, would you make a ranking? What is most important word in this sentence? Just based on your common sense. What is the most important wording? I. You think you are okay? What is second? Boy. Boy or girl. Third one? M. 4. This kind of scoring, I don't know, somehow we have long history of learning and training individually. Now we are talking each other. And we are making ranking of these wordings in a sentence or in a book. That kind of scoring process is called self-attention. There are some ways to make a ranking. One of them is Q, K, V. You remember we have input X, and you remember we have position information, and this information will be multiplied by QKV. QKV is a kind of ranking among the words in a sentence or in a book. So this is self-attention. Usually it is hidden inside encoder. Of course, in the future, decoder may have self-attention as well. So this QKV is a matrix, huge size of matrix, like a million by million matrix. The training process of this transformer model is to determine QKV, who generate the minimal loss function. Because so many weeks we have been talking about loss function with entropy, cross entropy, and K divergence, and so on. So we are not going to go details. But our given is X and P, position. Output will be those will be the input. Output will have certain best answers. If this English, output is Korean, maybe there might be some references to compare. This output will be compared with the reference, and we can define loss function. And we're going to have back propagation to update QKV. Input is X added by the information of position. So these three matrices are key of attention, core part of attention. In order to understand the basic principle of transformer model, you have to understand attention. And in order to understand attention, you have to understand QKV vector. The main focus of class today is to explain you what is Q and what is K and what is V. And similarly, in the cross attention, we also can define Q, K, V, and we have to train them. Actually, there might be many ways to explain them, but I think by having some multiplication of QKV vectors, we can make scores. Who is important, who is neglectable, and so on. Second mechanism is cross-attention. This may be encoder embedding sequence. This is decoder, the embedding sequence. You have to make a map to know who is important, who is less important. We have to make a score. Let's assume that this we have a sentence. 현아, let's make a scores. Let's assume we have a wording at the decoder. Would you make a ranking among four? Who has more significance associated with the KAIST? What would be number one? Student. Number two? So, number one. What is number two? Number three, 4. This is cross-attention. Of course, in this example, we have only 1, 2, 3, 4 wordings, but in real book or sentence, we may have thousands or millions. So it makes long time. This matrix size may be much, much bigger than we can expect. So cross-attention means here we may have input X and output X dash, and we also can define QKV. That is to make a relationship between embeddings at the encoder to embeddings at the decoder. I think somehow you and I have very common ground. When I prepared this class note, I thought, yes, KAIST is a place for students. Among them, I'm important. Sometime I was a student, I'm going to be a student. There are many different ways, but I think the most important thing is myself is a student at KAIST. Then right now, and there might be 10,000 students, I'm one of them. So logically we can make some scores. But during the training process of transformer model, we are not teaching them the logic. They just read so many books and so many texts in the internet, and they somehow was able to make a scores. And then after training, we train QKV vectors somehow, and we input certain sentences, we have proper output sentences. And they are speaking like a human being. We cannot actually distinguish AI, GPT, and human. That is a little bit weird, but there is power of computing. Right now, as I mentioned before, encoder is operating with the parallelism, so instantaneously we calculate self-attention. But when we are calculating cross attention and decoder operation, output will be a sequence one by one. That was shown up in the paper. Attention is all you need to know. If I'm a CTO at OpenAI, I would like to develop decoder who can generate output in parallel. And if I have Elon Musk and AIX, I would like, right now, this GPT-X has input of text and output is text. And maybe we can convert, we can put some transformer like voice to text and text to voice. So we can freely talk to the ChatGPT. But somehow, some people will develop a new transformer model where if we have an input text, output could be a sequence of image or sequence of sound, then we can make a movie. With a sequence of text associated with a sequence of image and sound, we can make a movie. I think that could be GPT-7 or 8. Probably computing power, supercomputing and GPU power has to be 1,000 times more stronger than right now. So a lot of money is put into that direction. Now, let's move in a little bit further. I would like to talk about encoder architecture. As I mentioned before, transformer model that is used for GPT-X, it has encoder and decoder. Encoder has parallel input and parallel output, and output will be connected to decoder through cross attention. And between these wordings inside the encoder, the connection between wording will be represented by self-attention. So right now, I would like to go a little bit deeper into encoder. As I discussed before, attention will be described by Q matrix, K matrix, and V matrices. Probably at the end of the class, I'm going to go a little bit deeper into what is Q, what is K, and what is V. In encoder, it may have certain number of steps of self-attention. This number of NX could range from 1 to 10 or more. Probably if you want to develop transformer model for more multimodal or more complicated one, NX may increase. Of course, it will increase the amount of computation and it will increase the amount of time delay because we have to move more by more. Of course, each self-attention, we have QKV. This huge matrix has to be trained during the backpropagation. We have input X1, X2, up to xt. As I mentioned before, this x1 to x2 will be input to the self-attention in parallel, simultaneously. In RNN, we put x1, x2 up to xt sequentially. But here, very important thing is we have to convert x1 to w1, w2, and wt. This process is called word embedding. There might be many different ways to make a coding of our wording. Each word may have some distinctive coding 001, 002, 003. There might be many different ways. And also, we have to add position information. Positional encoding will be added to initial wording. At the third class of this, at this transformer module, I'm going to talk about how we can add position information at this input wording. Based on my definition, this W is called as token. Word embedding with positional encoding can be called as a token. So depending on GPT-X evolutions, this token number will increase. Depending on how much money you put for the membership of OpenAI, you may have different amount of token when you are putting the input and output. I assume in GPT-5 or 6, we can put whole book. If you pay $100 in a month or something like that, then in a millisecond, whole translation of your book will be in Japanese, Chinese, Korean, English, French, and so on. So human translator may lose their job, or they may check the final, they may work at the final stage to check errors, something like that. So first draft may be done by transformer model. So if you have token, you can calculate Q1, K1, V1. By multiplying this word embedding, by multiplying token, Qi can be obtained by Q matrix by Xi. Ki is multiplied by K matrix with the word embedding. Vi is V matrix multiplied by Xi. With the given K, Q, K, V matrices, that has to be trained during the backpropagation. But at certain moment, we have Q, K, V. By multiplying Q with the input embedding, either sometimes I can say it is W1 or X1, whatever, we can calculate Q1 vector, K1 vector, and V1 vector. By multiplying with next token, we can also calculate Q2, K2, V2. And at the last token, we have QT, KT, and VT. Please remember that Q, K, V is a kind of matrices that express the degree of importance of self or mutual. Q is more likely self-importance, K is a kind of mutual importance. V is a kind of adding these two effects, self-importance and mutual importance, adding together, we're gonna have finally value. And by having this QKT, these numbers will be the input of the self-attention, and we're gonna have output. This output is updated token. This is my explanation. You have input wording and you add some positional information that is becoming token. Sequence from W1, W2 to WT. By applying self-attention mechanism, we're gonna update the token. And by matrix calculation of QKV, we can generate Q1, K1, V1, Q2, K2, V2, QT, KT, VT. At this moment, it is a little bit difficult for you to follow up, but after a certain number of classes, you feel more comfortable, I think. And later on, if you need to know more about this, you can use transformer model for your homework or term project, or you can read this paper whose name is Attention is All You Need. Let me summarize the encoder architecture in the transformer model. As I mentioned before, the transformer model has encoder and decoder. And among the wordings inside encoder, they are using self-attention mechanism to make scores of each wordings, how much it is important how in self and how much it is important between the words. And so it is a kind of attention mechanism inside the encoder. Now, decoder will generate output serially, and decoder and encoder relationship will be defined by cross attention. So because of that, attention is very important concept. Firstly, applied in transformer model. Previous large language model has different type, encoder, decoder, and in the middle we have latent vector space. So because of latent vector has certain amount of limitation in terms of size and sequential summarization of previous effects, sometimes the first sentence or first wording effect is very diminished. So those are the previous large language model, but in transformer model, they are using attention mechanism. And by using the attention mechanism, we pay attention to the word at the first word in the sentence and last word in sentence. Also, between the relationship between output at T dash last wording has some connection with the first wording in the input that is defined by cross attention. So by having cross attention, we can reduce the memory, long-term memory effect. Also, by applying the self-attention mechanism, we can achieve the parallelism, especially at the encoder. Now, let's go a little bit deeper into the encoder architecture. And I can say is that encoder has certain number of stack of self-attention. It doesn't need only one attention, it has multiple attentions. And later on, I can tell you that when I define a relationship with our students, there are certain ways to define them. First, same office, same research area, and professor and student relationship. Also, there are also same high school or same religion. Or when we are defining this self-attention, there might be many ways to do that. In terms of history, who is important? Sometimes location. There are some wording who has the, we can make a scores, but we can make a scores with many different perspectives. Relationship, location, job, or income, amount of income, how many children married or unmarried, or his style. There might be many different ways to make a scores. That is called as multi-head attention. This QKV matrix is not the single one. There are multiple matrices. That is called as a tensor. So to make more complete connections, later on I will tell you this transform model are using multi-head attention. When they are making scores, there are many different standards to use. GPA, height, weight, or living style, or religions. There might be many different ways to make a relationship and make a score. So this QKV vector has multi-dimensional. Let's assume that initially 2 by 2 matrices, 2-dimensional matrices. By adding different subjects, we can have tensors. Actually, the size of this matrix T by T multiply this multi-dimension. If we have a time sequence up to T, this Q matrix, K matrix will have a size of T multiplied T. But also we have many different matrices. So depending on how you define the hyperparameters of transformer model, we may have more and could be increased. Also, this attention, multi-head attention is not just single layer. It may have more layers to add more meanings between the wordings. And NX could range from 1 to 10 or 100. This is actually deep learning. Layer is becoming deeper and deeper and deeper. And if you increase the multi-head attention number n, also it will increase the number. All is about, I think the title of this paper is Attention is All You Need. Probably next wording, if I have to decide, is the computing is all you need. Parallel computing is all you need. So in the paper, they are using the word token. So if we have sequential input, position will be added, and that is becoming a token. And at each token, we can calculate query, key, and value. Later on, I will tell you how we can calculate this one. And that will be the input of self-attention. And by multiplying some matrices, let's assume initially I am a boy. After a first attention, I think I am a boy. Even though it is the same token, the height of each wording may be different depending on how we can define the self-attention. Because I give you a big size writing of boy because it may have higher score. Jungmin told me that this is the most important. So it propagates through self-attention layer, and finally we got a certain output. I don't know, sometimes it is very difficult to figure out what this number means, but those numbers will be used to feed cross attention to the decoder, and decoder certainly have some output, and it is very difficult to distinguish between human and transformer model. Let's assume that our input is x1 to xt. Somehow it is interesting. I don't know. I haven't tried it yet. But all these numbers are real numbers. They are not using complex numbers. And sometimes I will try to explain why neural network only use the real numbers. It doesn't use the complex numbers. But when we are analyzing the electrical circuit or electromagnetics, we represent them as a superposition of sine waves. And when we are superpositioning the sine waves, we have to add some phase delay effect. And phase delay is represented by complex numbers. So we can usually analyzing the differential equation of sine and cosine waves using the complex numbers. But somehow, all these numbers are just real numbers. Interesting. If you can define a new transform model using complex numbers, you may get Nobel Prize, probably. So this matrix means at this moment, here is the kind of graphing method to explain the encoder architecture. Now I would like to use some mathematical description of self-attention. This is not rigorous way to do that, but it is easy to explain to you. The size of input vector has certain dimensions. As I know, I might be wrong. At this moment, each input token has 522 bits. So at each propagation along this self-attention in encoder, the size of vector of each token will be represented by a vector of 512 bit size. In the future, let's assume that you're going to put images sequentially, x1. In a movie, we have how many screens in a second? 36, 18? Tetsu, can you tell me how many shots we have in a movie or television? 60 frames in a second. Okay. Then 1 hour movie has 60 multiplied by 60, huge number. So this sequence may be huge. But each screenshot, one image has certain large vector size. 1,000 times by 1,000 times. Anyway, during ChatGPT 3 and 4, as I remember, each wording token is represented by 520 bits. So amount of information we can describe using this vector is 2 to 512. That's huge number. Of course, we have to add positional information as well. Some languages, Korean, English, Japanese, Chinese, so sometimes 512 bit may not be enough in the future. And time t step may be huge. 1 to t could reach a millions in the future. And then we may have matrix multiplication x multiplied by k the first matrix token has a size of matrix T multiplied by D. You remember this is 512 and this is the size of sequences multiplied by query matrix. And this query matrix has size of D by D, so it's going to be 512 by 512. We're going to have Q1 to QT. Query, Q means how much I'm important. K means how much I'm important to others. So this is more like the relationship between other sequences, and this Q means the importance to himself. As I mentioned before, at each steps of token, updated token, before token, and so on, after or before the self-attention, we have to calculate query, key, and value. How can we do that? We have to multiply by input sequence multiplied by query, that is going to be Q1, Q2, QT. And again, I want to emphasize that this Q matrix and K matrix at each attention step has to be trained. In multi-head attention, we are not pursuing only single Q or K. At each head, we may have different Q value and K value. At each self-attention level. Next self-attention level, we have different K, Q values. Right now, I'm telling you that how can we calculate Q carry vector, key vector, and value. Now, first step is we have to calculate this query. Number two is we have to calculate the key by multiplying query and key. We can obtain this new matrix. I would say this is score. And output is going to be softmax X is token. At the moment, we have carry that describes the significance of itself. X is token, K is the significance between the wording, how much I'm important to others. Multiplying by them, we have certain scores. So score means how much I'm important to myself and how much important to you. They are multiplying them together. If I'm useless, it is becoming multiplication of token multiplied by Q is gonna become 0. Then output score will be 0. Even though I'm important to myself very much, Hyuna believes that I'm not important, then carry score will be 0. Don't do that, okay, until you graduate. So depending on time sequence, this value might be different. At the beginning, when Hyuna came to my lab, I'm very important. After graduation, I'm not. I don't like that kind of sequences, okay? I like more likely at a time sequence, I become more and more important because we are building up more experiences and good emotions and confidence in each other. We make a better people. Initially, score might be 0. Output will be 1. Why I'm saying maximum is 1? Because we have softmax. Even though I'm good, very good to myself, if Jungmin think professor is not good one, my key score is 0, then output will be 0. That's why we have multiplication in matrix. And if I am very good to all of them, like we have 20 students, and this softmax means 0.1, 0.1, 0.1, and all the summation will be 1. That's why softmax has. And this V means value. It's a kind of previous value, and they update my value. This first self-attention is my significance at school. Second self-attention is my significance at home. Third self-attention might be significance to my friend. Last one is significance to golf course. At the golf course, has the highest attention. Now, this is the end of the first class of transform model. I'm sure that it is not easy to follow up, but I would like to give you my best to give you all the perspective of this transform model. As I told you before, transformer model has very important features. Transform model is used for GPT. Number one is it is pushing parallelism for real-time response. And second one is, in order to do that, input has to be progressed in parallel. How can you do that? We define this relationship, especially the key. Rather than doing sequentially, they just calculate in parallel. How they make a relationship between first and last by positional encoding and attention. And the last one is positional encoding. Later on, I will give you more details. So this is the very brief overview of transformer model, and attention is one of the most important but very difficult to understand. I would like to give you the idea about the attention, especially at the encoder. And next class, I'm going to go a little bit deeper and deeper. Thank you for your attention, and please be patient. And after a certain number of classes, you will be more relaxed. Thank you.